This video is going to run through some of the basics of rational functions. And rational functions are algebraic fractions. So we're going to be considering functions that look like fractions, have numerators and denominators, and the numerators and denominators are going to be polynomials. So let's start by considering one of our simpler rational functions. This is our reciprocal function, f of x equals 1 over x. I have drawn on the screen the graph of this function. I graphed this by plotting points. For example, if I put in 1 for x, I get y equals 1. So the graph goes through the point 1, 1. If I put in 2 for x, I get y equals a half. If I plug in 3 for x, I get y equals a third, and so on. So let's take a minute and talk about some of the features of this graph. This graph and this function has a domain of all real numbers except for x equals 0. I can see that in the equation because I know division by 0 is undefined, so x cannot equal 0. And I can also see that in the graph. This function exists for all values of x except at x equals 0. We can also talk about some of the behavior of this graph by introducing some new vocabulary words. As the x values are getting closer and closer to 0, for example, if I plug in x equal a half, I get a y value of 2. As those x values approach 0, those y values are going to go up towards positive infinity. If I approach 0 on the left, picking negative numbers that get close to 0, the y values go down towards negative infinity. We call this behavior a vertical asymptote. This graph has a vertical asymptote of x equals 0. That means as x approaches 0, the y values go up towards positive infinity or down towards negative infinity. The y values increase or decrease without bound. This graph also has a horizontal asymptote that describes the end behavior here. As the x values go towards infinity, as we go towards the right, the y values are approaching 0. That happens on the left as well. As the x values go towards negative infinity, the y values are going to 0. So we describe that by saying we have a horizontal asymptote of y equals 0. As x goes to plus or minus infinity, the y values go to 0. So let's break down each of these components in a little bit more detail. We'll talk about domain, vertical asymptotes, and horizontal asymptotes. So let's start with domain. If we want to find the domain of a rational function, we just have to look at the denominator, and that denominator can't equal 0. Division by 0 is undefined. So my first example, the function f of x equals 2x plus 3 over 5x minus 6, I just look at the denominator, that cannot equal 0. So if 5x minus 6 doesn't equal 0, then x cannot equal 6/5. And my domain is everything from negative infinity to 6/5 and 6/5 to infinity, not including that 6/5. Same idea holds for my next two examples. I have the function x minus 3 over x squared minus 9. I just look at the denominator. X squared minus 9 cannot equal 0. I could solve this one by factoring. X squared minus 9 can be factored as x plus 3, x minus 3. So that tells me x cannot equal plus or minus 3. In interval notation, that's everything from negative infinity to negative 3, negative 3 to 3, and 3 to infinity, not including that negative 3 or 3. And finally, in my last example, x squared minus 4 over x squared plus 1, that denominator can't equal 0. So if x squared plus 1 does not equal 0, that means x squared cannot equal negative 1, and that has no real solution. So this is telling me that the denominator is never equal to 0. If I plug in any real number, I will never get 0. So in this case, My domain is all real numbers. All right, how do we find vertical asymptotes? Finding vertical asymptotes is really similar to finding domain, with one kind of important difference. So let me first go through the steps, and then I'll show you some examples. To find a vertical asymptote, we're going to factor our numerator and denominator. We're going to reduce, so cancel out common factors, and then zeros of the denominator in this simplified function are vertical asymptotes. If there was a common factor, zeros of that common factor are actually holes in the graph or removable discontinuities. All right, so here's two examples. We're going to find all vertical asymptotes. So it's similar to domain in the sense that we're looking for zeros of the denominator, but a little bit different in that if there's a common factor, that changes things. So my first function is f of x equals 3x over x squared minus x minus 2. I can factor that denominator as x minus 2, x plus 1. Let's just double check that. Minus 2 times 1 is minus 2. Minus 2 plus 1 is minus 1. Yep, that's factored correctly. In this case, there are no common factors. I cannot reduce this, so I just set my denominator to 0. That means either of the factors, x minus 2 could equal 0, or x plus 1 could equal 0. And that means I have two vertical asymptotes, one at x equal 2 and one at x equal negative 1. My second example has the same denominator, so we've got this x squared minus x minus 2. I can still factor that as x minus 2x plus 1. But now I have the numerator x squared minus 1. That's a difference of perfect squares, and it can be factored as x plus 1, x minus 1. This time, I have a common factor of x plus 1. So when I find my vertical asymptotes, I have to ignore that common factor. That's not going to give me a vertical asymptote. So in this case, I'm still looking at the denominator, but now I only look at the x minus 2. X minus 2 equals 0 when x equals 2, so I only have one vertical asymptote. However, and this is how finding vertical asymptotes is different than when you're thinking about domain, this x plus 1 still tells me that x cannot equal negative 1. Negative 1 is still not in the domain of the function, but it's not going to be a vertical asymptote. Instead, it means we actually have a hole in the graph at x equal negative 1. These holes are sometimes referred to as removable discontinuities. All right, how do we find horizontal asymptotes? Horizontal asymptotes are describing end behavior. And so to find horizontal asymptotes, there's three different cases, three different things that can happen. And to figure out which case we have, we're going to consider the degree of the numerator, so the largest exponent in the numerator, and compare that to the degree of the denominator, or the largest exponent in the denominator. In this example, the degree of the numerator is 1, of x to the 1. The degree of the denominator is 2, because we have an x squared. The numerator has a smaller degree than the denominator. Whenever that happens, whenever your numerator has a smaller degree than your denominator, your horizontal asymptote is always going to be y equals 0. Basically, what's going to happen is as x goes to infinity, when x gets really, really large, the denominator is going to grow faster than the numerator, and you're going to end up dividing by something that gets bigger and bigger and bigger more rapidly, and your y values are going to go to 0. So anytime the degree of the numerator is smaller than the degree of the denominator, our horizontal asymptote is y equals 0. Okay, if the degree of our numerator is equal to the degree of our denominator, so in my example, the numerator has the largest exponent of 2, so degree of 2. The denominator also has the largest exponent of 2, so degree of 2. So the degree is the same for the numerator and the denominator. To find the horizontal asymptote, we basically take the ratio of the leading coefficients of the numerator and denominator. Okay, so what that means is you look at your leading term with the largest exponent in the numerator. That has a coefficient of 2. Your leading term in the denominator has a coefficient of 1. So your horizontal asymptote is going to be 2 over 1, or y equals 2. So that means when x goes to plus or minus infinity, your y values are going to approach 2. Finally, if the degree of our numerator is bigger than the degree of our denominator, so in my example, the numerator has a degree of 3, the denominator has a degree of 2, so numerator is bigger than the denominator, that numerator is going to grow faster than the denominator. So as x goes to plus or minus infinity, your y values are going to also increase without bound. This means you don't have a horizontal asymptote. So no horizontal asymptote. So let's run through a little bit of practice. Find the horizontal asymptote of each. My first example, f of x equals 6x plus 3 over 5 minus 2x. Both the numerator and denominator have degrees of 1. This is the case where we have the same degree in the top and the bottom. So we're going to take the leading coefficients, and that's going to give us our horizontal asymptote. The leading coefficient in the numerator is 6. In the denominator, it's a negative 2. So y equals 6 over negative 2, or y equals negative 3, is my horizontal asymptote. Here's my second example. F of x equals x squared plus 1 over x to the third plus 5x. The numerator has a degree of 2. The denominator has a degree of 3. The numerator has a degree that's smaller than the denominator, so y equals 0 is my horizontal asymptote. One more example, f of x equals x squared plus 2 over x plus 3. This time the numerator has a degree of 2, and the denominator has a degree of 1. Since the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. I want to take a minute to kind of talk about, well, what happens in this third case where there isn't a horizontal asymptote. It turns out there's actually a slanted or oblique asymptote, and I can explain what that is, how we find that, and what that looks like. So if I actually do this division, so I'm going to take x squared plus 0x plus 2, and I'm going to divide it by x plus 3 using synthetic division. So I'm going to jot down negative 3 outside of my box. Bring down the 1. 1 times minus 3 is minus 3. I add. Minus 3 times minus 3 is 9. I add. I get 11. So according to synthetic division, this function is the same as 1x minus 3 plus, here's my remainder of 11, over x plus 3. This 11 over x plus 3 is that case 1, where the degree of the numerator is smaller than the degree of the denominator. This remainder, when x gets really, really large, is going to go to 0. And so the quotient, this x minus 3, is actually our asymptote, or our end behavior. So the line y equals x minus 3 is actually our slant asymptote. And if I graph this function, if I use technology to graph this function, I can actually see that the ends of this graph look like that slanted line, y equals x plus 3. Okay, back to discussing our rational functions in general. Let's see if we can put together everything we've talked about in this video. Let's find the domain, let's find the asymptotes, and then sketch a graph. To find the domain, I know that the denominator can't equal 0. So x plus 3 can't equal 0. That means x cannot equal negative 3. My domain is all numbers except for negative 3. Vertical asymptotes. There's no common factors. X plus 3 equals 0. So x equal negative 3 is my vertical asymptote. So I just set the denominator to 0 to find my vertical asymptote. Horizontal asymptotes, this is the case where the degree of the numerator is the same as the degree of the denominator. The numerator has a leading coefficient of 2. The denominator has a leading coefficient of 1. Y equals 2 over 1, or y equals 2 is my horizontal asymptote. All right, so I'm going to put this onto a graph. I'm just going to lightly sketch in a line at x equal negative 3 and a line at y equals 2. Those are my asymptotes. Then I'm going to plot some points, and to help me, I'm going to actually find my intercepts. My x-intercept is when y equals 0. The only way a fraction can equal 0 is if its numerator equals 0. So I have to figure out when does x minus, or said that wrong, when does 2x minus 2 equal 0? That occurs when 2x equals 2 or x equals 1. So I'm going to put on my graph, I have an x-intercept at x equal 1. Now I can kind of start to draw this. As the graph goes to the right from this x-intercept, it has to approach that horizontal asymptote. So I'm just going to draw something that approaches that line, y equals 2. From this x-intercept, as I move to the left, the graph is going to have to go down towards that vertical asymptote. So it's going to go down towards that vertical asymptote of x equal negative 3. Since there are no other x-intercepts, the graph doesn't cross the x-axis any other places, I know the rest of the graph has to lie above that horizontal asymptote. If it were to lie below the horizontal asymptote, then it would cross the axes. But I don't have any other intercepts, so I'm just going to put something above those asymptotes. As I go to the left, approaching y equals 2. As I go to the right, it goes up towards that vertical asymptote of x equal negative 3. Let's run through one more example. Same thing, domain, asymptotes, graph. So denominator can't equal 0. That means x squared minus 9 cannot equal 0, and x cannot equal plus or minus 3. To find my vertical asymptotes, I factor, and I notice there's a common factor of x plus 3. That means I have only one vertical asymptote, and that occurs when x minus 3 equals 0, or when x equals 3. At x equal negative 3, there is a hole in the graph or a removable discontinuity. Horizontal asymptote, this is the case where the degree of the numerator is 1, the degree of the denominator is 2, so y equals 0 is my horizontal asymptote. I'm going to sketch some lines to indicate my vertical asymptote is at x equal 3, and my horizontal asymptote is at y equals 0. Does this function have any x-intercepts? Well, if I set the numerator equal to 0, I get x equal negative 3, but that's not in the domain of the function. Negative 3 gives us a 0 in the denominator, and so there are no x-intercepts. All right, so then to sketch my graph, I would like to put a point on it, so why don't I find the y-intercept? If I plug in 0 for x, I get y equals 3 over negative 9, or y equals negative 1/3. All right, so then this function, here's my y-intercept. As I go towards this vertical asymptote, it has to go down. I know it doesn't go up because there's no x-intercepts, so it has to go down. And then as I go to the left, I'm going to approach that horizontal asymptote, and I'm going to draw a hole at x equal -3. For the other part of the graph, I'm just going to plot a point because I'm not really sure where the graph is this time. So I'm going to just plug 4 into this function. I got 4 plus 3 is 7 on the top. 4 squared minus 9. 16 minus 9 is also 7, so I got y equals 1. So when x is 4, y equals 1, I've got a point. And then by plotting this point, I know that because there's no x-intercepts, the graph can't go down. It has to go up towards that vertical asymptote. And then it's also going to approach that horizontal asymptote as we go to the right. And there's the graph of my function. All right, that was my last example. As always, if anything's unclear, please let me know.